Good Friday morning, everybody. This is Ian Trevethan. I am the Education and Outreach Manager here at the Sternberg Museum of Natural History, and we're kind of switching gears here today, and we're going to kind of do more of a Fossil Friday for our live feed. And I am really excited to have our Chief Curator and Professor of Paleontology, Dr. Laura Wilson, in the Paleo Lab, sort of talking about, we're tying this to our current exhibit, which is Into the Arctic. And I think we're going to do sort of a two-part series here, maybe more if you're up for it.
We'll start with two.
But I thought it'd be really exciting for people to get a chance to talk to somebody who's actually, you wear so many hats.
Yeah,
In our institution. So you're the curator of collections here.
So yeah, I have a couple of titles. The one I usually use is curator of paleontology.
Okay.
Since I'm a paleontologist, that's really where my focus is. Technically, I'm also the curator of geology, so I oversee our small but growing and recently improved.
Hat number 2 there.
And then within that role, I'm also the chief curator. So in that sense, I do oversee the collections managers, the associate and adjunct curators. And
so those are 3 hats in the museum itself. What are your other hats elsewhere?
So I have a really interesting position at Fort Hays, which I love. It's having 2 separate jobs, but I get to have my fingers in everything, which is great. So half my appointment is here at the Sternberg Museum, and the other half is in the Department of Geosciences on the main campus of Fort Hays State. And over there, I'm an associate professor. So I teach, 2 classes a semester, advise undergrad and grad.
So there's the teaching aspect, which is challenging, but then there's the advising aspect, which is challenging.
That's always interesting.
So I wanted to kind of cover those bases just for anybody out there that is kind of wondering what a paleontologist does from day to day. Because, when I started in the paleontology field, because that's my background as well, I had no idea. And I remember a certain advisor I was working under telling me that, if you want to be a professional paleontologist with a PhD, you're going to have to do all these things. Mm-hmm. And you do research as well.
Right.
So paleontologists don't just go out and dig things up and bring it back to the museum and clean them. And there's so much more going on.
Yeah, it's very few people, very few paleontologists actually get paid to collect fossils.
Yeah.
If it's written into their contract, which again, very few are, and it's usually museum-based that have that field collection written into their contracts, it's what you do in your summer. So if you're a typical university professor, your contract's 9 months of the year. So you have that summer off, but that's really when you're slamming the research, and a lot of those are grant driven. So applying to National Science Foundation, or based foundations to get funding to go into the field.
So you're not getting rich doing this?
No, it's a labor of love, but you also get to do what you want to do. Yeah. And there's a lot to be said for job satisfaction.
Absolutely, and I can attest to at least part of that. Because I've gotten to do those things over the last 15 years myself, and it's much harder than I ever thought it would be, but it's also a way more rewarding than I ever thought it would be. So that's great. Where am I going with this? I'm trying to segue into so you've had a rough year actually, because you were not only all of the things we talked about, but you were basically acting department chair for your geosciences department at Fort Hays State University.
So it's interesting. The past year I've taken kind of a official, unofficial leave of absence from the museum because I stepped into the role of interim, so temporary department chair for geosciences. And that was a great learning experience. I loved the museum and the museum aspect of my job, so I knew that doing that long term wasn't going to be what I needed to do.
But in reality, you were not absent from the museum, because I saw you.
Yeah.
So,
but there wasn't as much research that was done, and I didn't have my hand. I left my students, and I left collections kind of in
Right.
charge of other people and was just doing a little bit more consulting and
So,
lighting.
on the back of that, the reason I
Yeah.
bring that up is because now you've come to the end of that,
Right.
and you are taking a sabbatical.
I am.
And
Very
that
excited.
allows you to do research.
Right, so I'm doing a
So-
research-based sabbatical, which means that, I really get a focus on kind of the research portion of my job, but it's not just my research and my projects, but it's also getting things set up for new graduate students or new undergraduate students. With all of my different hats, the hardest thing I have to fit into my schedule is research, whether it's for me or whether it's advising students in their research. So to be able to take a couple of months and get ahead and get a couple of projects just off the ground so that I can more easily incorporate students as they come in or ask to work
Right.
with me, then it kind of makes it easier on everyone.
So you're going to at least take some of this time to sort of help get student researchers set up, maybe get them some training, that kind of thing.
Right.
So, having said that, let's lead into what your I guess special focus within paleontology is.
So you kind of, it's a pyramid or, a Venn diagram, however you want to see it, and you just get narrower and narrower, the more as you get into it. So I'm a paleontologist. Within that, I'm a vertebrate paleontologist, meaning that I study animals with bones. Within that, my main focus is on paleoecology. So if I had to define myself, it would be as a paleoecologist, because I'm really interested in ecosystem structure, so how organisms interact with each other as well as their physical environment.
So, what these
Food webs.
what these things ate, how they interacted with, the changing
Right.
factors within their
Right. So, and then within that specifically, I've been working for, the last several years, 12, 15
It's
years.
a little scary when you stop
I
and
think
count those years.
14, 15 years. I've been working within the Western Interior Seaway. So Kansas specifically, this is a perfect place for me because I'm really interested in the ecosystems of Kansas 80 to 100 million years ago. So when Kansas was covered by the Western Interior Seaway and we're an ocean, so who's eating whom, the effects of temperature and climate change and the effects of ocean currents on different ecosystems, how that changes
So
up
I'm
and
going
down the
to
seaway.
throw this at you. Why is that important? Why is it important for people like us in the museum to worry about what the ecosystem was like 80 to 70 million years
Right.
ago?
So, I think there are two main things that I typically point out. And the first is paleontology as a whole. So paleontology is very much this kind of pure science that we're not curing cancer, we are pushing the envelope of knowledge and adding to that. But I think one of our biggest roles is the fascination factor. And I always say that we're the gateway drug to science. And, the Sternberg Museum embodies that perfectly because we have such a big paleo component. Those are the natural resources we have in this area. Those are the resources we have in our exhibits and education programs on. And that's what hooks the kids, in terms of these big, fascinating animals that we have, the mosasaurs and the fish within the fish. And, you go to some places in Kansas and outside we get the dinosaurs and all of these things that just evoke this fascination and that encourage people to ask, why, how, what is this, and how do we know?
Do you think there might be some application of tracking climactic change
For
in
sure.
these systems
Yeah.
and applying it to, at least to some extent, and understanding what's happening with our
Right. So
current
that's the
ecosystem?
second aspect. The first is getting people interested in science and asking those questions, encouraging them to be lifelong learners. The second part is that we can look at these ancient ecosystems as experiments that have already run. And so we can look at them, we can look at the animals, we can look at our different climate proxies, whether it's stable isotopes, whether it's the plants and animals that live there, whether it's specific animals and how they relate to temperature or salinity, things like that. And we can look at these different parameters and look at how those ecosystems change. So if temperature goes up, we can see how the animals change. We can see how how other aspects of the climate change. Temperature goes down, we can look at that. We can look at how animal ranges change. We can look at the evolutionary processes.
So in ocean systems, when we're talking about temperature and salinity values, they work together.
Right.
So generally, if the water temperature is cooler, the water will be less saline or salty. Where it's warmer, it tends to be a higher salinity level or sort of a more of a salty kind of water. And there are a lot of animals that are sensitive to those kinds of things. So that's what helps researchers like yourself sort of track some of these things.
Right. So, I mean, all the research that I do in, Mesozoic ecosystems, I directly compare to modern analogs. And a lot of times there aren't modern analogs. So you're looking at why aren't there modern analogs? What was so different 80 million years ago that we don't find the equivalent today? But, if you think about climate research, and we're always hearing about models. So those models are built in a lot of different ways. And one of the biggest powers of science in general is its power to predict. And so that's what we're doing with climate models going forward, is that we're taking different climatic parameters today and trying to recreate through our algorithms what climate's doing today. And then we can track that to what we know against the past and see if we can recreate those past climates.
Rather than forecasting, we're hindcasting.
We are, but then when we get a model that fits the present and we get a model that fits the past, we can use that model to predict the future. So if CO2 goes up, or if methane goes up, or if water vapor goes up, we can see that. If ice caps go down, we can see that water levels.
So we can track action and reaction kinds of events through time.
And then we can use that to predict the future.
And then look at, similar things are happening, so we can predict that this is happening, or this may happen.
And that's the climate, but we look at range and animals and plants, how their change as different parameters in the environment change. And so we can see that if we see a range of an animal shrinking or migration patterns changing or constricting in the past, we can see what maybe some of the factors that influence that and use that again to predict the future.
So I have one more kind of tough question for you, and then we'll move on to some other stuff. But you mentioned that sometimes we don't have a modern analog.
Right.
And I definitely, as the case for the Western Interior Seaway that was over this part of the United States and North America, Kansas specifically. So when we're looking at animals or environments or ecosystems that existed in this seaway, is there a modern analog that you can think of to
there's certain aspects of it. The Western Interior Seaway is so unique because it is an epicontinental seaway, meaning that it is a flood net. We're standing on what was the seafloor, and the ocean never got very deep. We're talking, 200 meters. Pretty shallow. There are a lot of unknowns about it. We don't exactly have a good handle on the circulation patterns. We don't know how brackish it was, so how the freshwater or hypersaline, so a lot more. We don't know what the salinity was. So there are a lot of question marks. So I was kind of talking earlier about how you kind of scaffold into your little specialty and you get to that top. So I do Western Interior Seaway paleoecology. And one of the animals that I've really focused on for the last, 16, 15 years, whatever it's been, is a group of birds.
Okay, we're back.
Okay, we're back.
So back to Hesperornis.
Hesperornithiformes.
Hesperornithiform is the larger group, and then the genus within it, one of the ones that I study is Hesperornis.
Excellent.
And we have a great example on exhibit here, and a few more bits and pieces in collection downstairs as well. And so these are really cool, goofy birds. They are foot-propelled divers. That means that they use their feet to swim. So
should we go look at one?
We can, if we want to.
Let's go look at one.
Migrate.
We're going to migrate. Oh, good segue word there. So this is what's great about being a person interested in paleontology and asking questions, even on a casual level. If you're just a person that lives in Kansas and happens to just be fascinated by this stuff, this is a great resource. You can come here and you can have a question about a thing that surrounds you. And I was going Yoda there, but surrounds you. And you can find some of these things. So I'm gonna let Dr. Wilson go ahead and sort of describe what we've got here.
Right. So this big one down here is Hesperornis. One of the cooler aspects of it is flightless. So if we look at kind of what's the pectoral or the shoulder girdle, we just see kind of little things that look like wishbones, and actually one of those is the wishbone. But they don't have very prominent arms. They have a humerus, which is the upper arm bone, but they actually have secondarily lost all of the bones. So the ulna and the radius and the wrist bones and the finger bones, they don't even grow those anymore because they don't need it. But they have these really long legs, and one of my favorite is this cool triangular bone. That's the patella, that's the kneecap. So they have these really long lower leg bones, little stubby thigh bones, and then this really long sacrum or hip. And that's just where all of these huge, powerful muscles attached so that they could kick through swimming. So a modern functional analog, a lot of the most recent research shows is probably like a flightless cormorant in terms of how it swam. And these are found in the ocean. They're really cool because they're very modern, foot-propelled seabird looking in one aspect, but then they're still dinosaurian ancestry with the long neck, and they have teeth, which is really cool. So I've done a lot with looking at these birds to get at what's going on in the seaway ecology. And one of the really interesting things is if you look at modern seabirds today, especially foot-propelled seabirds, so those that are kicking to pursue prey rather than something like a penguin, which actually flies underwater, so uses its wings, or an auk or a puffin, which does the same thing. So foot-propelled seabirds have interesting geography in that they stay very close to shore. They typically aren't considered as efficient swimmers as a wing-propelled diver. So wing-propelled divers, like our penguins and our auks, will go further out to sea, but they stay in cold waters. So we only find them in waters colder than about 15 degrees Celsius. And then the foot-propelled divers stay close to shore. If you then take what's going on in the seaway, we find these in Kansas, and so we're 200 kilometers away from shore. So we're finding foot-propelled divers in warm waters, which is different from wing-propelled divers, and far from shore, which is different from our modern foot-propelled divers. So we know that something different is going on in the seaway that's allowing these birds to go in ranges where we don't see similar seabirds today. And so the question is whether it's something environmental because of the nature of being an epicontinental sea and all of the nearshore environments and the shallow sea and the high productivity, or whether it's because there's a different ecosystem structure. So modern birds today have to deal with things like whales and dolphins, which we didn't have in the late Cretaceous. We had mosasaurs and plesiosaurs. And so whether, how these different factors go in to create something that we don't have a modern analog for today.
Well, and again, one piece of this puzzle sort of leads into another. So, you mentioned predator-prey interaction.
Right.
So instead of whales and sea lions and stuff, now we've got mosasaurs, plesiosaurs, sharks.
Sharks, we still have sharks.
We've always had sharks.
And big bony fish, but typically our fish that we have, like our tarpon and things like that are our tuna, which are big, big predators today. Things like Xiphactinus was a lot bigger.
Right. So, you're looking at, one very specific piece of this puzzle, but then there's a lot of other stuff like, okay, so you've got these predators. Well, how do these predators interact, within proximity to the shore? Are the bigger ones further out? And so one question kind of leads into another question, and it's very easy, and this happened to me, it's very easy to almost take on too much.
It is, and it's a very common problem but an issue that needs to be addressed in terms of how to scale a project reasonably.
Right.
And if you're working with an undergraduate student versus a master's student versus a PhD student versus building a career, There are a lot of different aspects, and it's always a discussion. Every student I've worked with, we've never had a problem of a project being too small. It's always been rein it in. That's going to be the follow-up. You can't answer that question until you answer this one.
So how often do you find yourself stepping back and going, man, I got to rein this in? Or have you kind of figured that one out through your career process?
It's gotten a little bit easier in terms of, figuring out with those bite-sized chunks. And I think part of that is because, with all of the different hats, I do have limited research time. So I know it's stuff that, okay, I got to nail this. But it's always the question of how much is enough. So my master's advisor, who you worked with for your undergrad, I think one of the best things he ever said to me is that no project is ever going to be done. That there's always something else you can do. There's always more data that you can collect. There's always another analysis that you run. But the most important lesson that you learn is when to stop and when to present what you have. And when you get enough data to answer the question.
So the cat's out of the bag there. We overlapped when we were going to college. She was finishing her master's while I was getting my bachelor's. So we kind of crossed paths.
We did.
A lot of years ago.
It is. And when I came out to interview for this job, I think I found out that you were starting work here just, like a week or two before my interview. You got in touch with me, and
it's pretty crazy.
Yeah.
So it is a small world.
Very small world.
So let's talk about your research specifically, your small bite of this big sort of world that we're trying to understand and sort of reconstruct. And how do you do that? What are the tools that you use?
So I have kind of two different avenues. I have the paleoecology and trying to put together these ecosystems. And sometimes in terms of what I'm interested in, it gets a little soft and fuzzy, or it's a gray area because it's very hard to go and collect data or quantitative data that you can analyze. A lot of it's comparisons, a lot of it's thinking about and working through different parameters. And the paper that I just wrote on what was different in the Western Interior versus now through the lens of seabirds was definitely the hardest project that I've ever worked on, and was very hard to get published.
And that, I guess, is a good cautionary tale when you're considering paleontology as a career path, that it's not as straightforward as digging up a skeleton and going, aha, it's this. Because the quantitative data, the amount of information we have to present to support a hypothesis is really dependent on geology, really.
I mean, it's dependent on so many things, and it kind of gets to the point that what we teach, from grade school up, is the scientific method, and that you do step 1 and step 2 and step 3, and you start with your question, and then you formulate your hypothesis, and then you gather data, and then you run your experiment, gather data, make your conclusion, and it's never that straightforward. There's a great diagram that the University of California Museum of Paleontology put out years ago that I love to show students, because it's a scientific method flowchart. And it's not a method, it's a process. And there's so much that goes into it in terms of data collection and analysis and reanalysis, and then somebody publishes something new or a new specimen is found, and you have to figure out how that fits in. And one of the things that we never really talk about until you get to college or graduate school and you're actually doing research and trying to get it published is the publication process. So you can write a paper, and it took me a year and a half to write the paper because it's just so much to get my head around, and then it took me that long to get it published. And so I wrote the paper and sent it off, and it didn't even get reviewed at one place. They said it won the right journal for it, so I got sent to a sister journal, and then I got reviewed there, and it didn't get accepted, and they're like, no, you need to go back to this first journal or change it and go this entirely other direction and put it in these journals. And then I changed it and incorporated all of the feedback from colleagues and sent it off again, and it kind of got rejected again with very similar feedback.
So what you're describing is, I really want to get to the histology lab, but one of the things that I'm hearing you say is, we start in elementary school where, you're given the scientific method and, you're kind of taught even, by the time you get to high school that you want, testability, you want repeatability, peer review is really important. But by the time you get certainly to the graduate level and beyond that, I'm sure it's even more specific, but we are trained to communicate these things in a certain way, write these things in a certain way, speak in a certain way, and sometimes it's hard for us to step back when we're communicating things to people out in the public. And I think that's become a problem, certainly in the last 20 or so years, because we're so used to communicating in a certain way. I mean, so the Journal of Vertebrate Paleontology, that was the format that I used as a student and a graduate student. And I remember taking, I can't remember, it was some sort of general writing class, and the instructor was blown away with the formatting requirements, for JVP format. She'd never seen anything like that
very
before.
Different than what you learn or do in an English class. Very different from journalism. Scientific writing is its own style, and it's very much just the facts, ma'am, and how much can I say in as few words as possible, and every word matters, and it takes a long time to read a scientific paper because there's so much to unpack. And that doesn't translate to somebody who hasn't been to school for 13 years for this one little specific subset of science, because I can read something on, something completely outside my research, but still within vert paleontology, and I'm still not going to get the paper.
Yeah, exactly.
The jargon is so specific. So there is a huge breakdown between scientific writing and communicating to colleagues and science communication. So communicating with, K through 12 school groups, the general public, advocational paleontologists and things like that. And I think it's something that, our generations, I'm a very old millennial. And so I think it's things that the more recent generations have really embraced in terms of working on the science communication aspect, and how can we get the pure scientific research and make it applicable or make it interesting or make it understandable
and that's
to the
important.
general public.
It's important in a couple of different ways. Number one, you want a general public excited about learning this stuff, but you also want to start looking at the next generation of scientists, of paleontologists for us. And we got to find a way to get these people excited and not necessarily intimidated by that this big leap from casual to professional. So that's one of I think our big goals here at the museum, is to make this stuff accessible.
Right, and I mean it was before I got here, but viewers who went to the museum back when it was on campus, before we moved into this building in 1999, it was a very different setup. It was curio cases with just specimens and artifacts and weird stuff that people had put in our collections on display, and it's really cool, and it was so much stuff, but there was no storytelling. And that's one of the big ways that science is progressing in paleontology. I think is one of the ones leading the front, because again, we're that gateway, is into storytelling. And so if you look at how the museum is set up now, there's a story and there's a flow, and we talk about the bony fish and look at these characteristics and think about what they ate, and now compare these two animals. How do they look different? How do you think that relates to how they moved differently?
And I've said this before. I've used the word story before in some of the other live feeds that I've done. And when I say story, I don't mean that we're sitting down.
You're not making it up.
Once upon a time there was a pterosaur. All of the storytelling we're doing here is based upon research. So it's not a fictional story. What we're trying to do is give you, I guess, a better word would be narrative of the world that was here 70 to 80 million years ago.
And my PhD advisor would always use kind of this is the story that I'm telling, and asking me what story are you telling through this. And it took me a long time to be comfortable with that word, because again, you're talking about story, and the first thing is fiction.
Well, and it goes back to the way we were trained to communicate, interpret, write, speak. So it's very hard to, on the other side, lose that, so.
Well, I think there's just always been this very strict and rigid format when we think about scientific writing, but all of the aspects are there. So one of the things that I always stress with my students is you have to tell what the purpose of the study is, and then you also have to say why it's important. Why is this relevant? One thing that my master's advisor would always ask is who's going to care? And that's part of the narrative, and that's part of the story. So one, you can look at it in this kind of very rigid structure, and then the other is the story of making sure all of the different plot points connect, because that's really important. You don't want to, throw in some secondary character that has nothing to do with the purpose of the paper. So.
And as an active museum educator, it's so much easier to give a tour when it's set up to tell that story or that narrative. So,
and it's interesting because you can tell so many narratives. When I give the occasional tour, I'm always very ecosystems, centered in my narrative, but you can do so much with functional morphology. So how the shape and size of an animal relates to how it moves.
That kneecap.
Yeah, I love the kneecap.
That kneecap. I get, it's funny when I have a school group here of fourth graders. I'm like, look at that kneecap. That is so cool.
Well, my favorite thing is to bring kids, adults, it doesn't matter, and ask them to try to identify what the bones is. So, where are the arm bones? Well, and they struggle, and I was like, trick question, they're not there.
Yeah, it's amazing what works for kids kind of works for adults. We're just big kids, really.
Yeah.
All right, so I keep saying I want to see what you do.
Yeah, I know, this is going to be like the longest.
This is the longest live feed ever, but you're getting a bang for your buck today. It's just not often that I get to see Laura here and actually talk with her while, she's got time. Like usually, she's like, I got 15 minutes, I got to be at a meeting by, so this is pretty cool for me. So let's go check out what you do. Explain to us what you do.
So I kind of talked about one of the aspects of my research and kind of this big picture paleoecology ecosystem thing. The other is a little bit more specific or less nebulous, a little bit more hard science, and it's dealing with histology. So we can start here actually. So we're right outside the fossil prep lab, and we have a couple of display cases where I've kind of thrown together some illustrations and information about what paleohistology is. So histology is the study of tissue. Specifically, I look at bone tissue since I really just care about things with bones. Unless you were talking about, like white wine sauce, and then I'll eat the shelly things.
Okay.
But what I do is, I take bone, or you can do this with teeth as well, and I cut it up, I mount it to a slide, and make it so that light can shine through. And I look at the microstructures. So, the blood vessels that run through the bone that bring nutrients, the cells that lay down new bone. A lot of animals lay down annual rings, kind of similar to a tree ring. And there's so much information you can get about how an animal grew, how an animal lived its life. And so this is another tool that I use specifically, and some of my students use a bunch of different tools that I use specifically to get at how an animal grew, whether we can see the effects of environment on an animal. I use this in my dissertation work to try to get at whether we could see whether an animal was migrating through bone patterns. And there's just so much information that you can get by looking inside of the bone that you just can't get from looking outside of the bone. So in addition to our prep lab, which is where we bring bones out of the field and clean them off and get them ready for exhibit or educational program or into our research collections, we also have a histology lab, so a place set up where we can process these thin sections or slides to get at this information, to look at how an animal grew from hatching to death.
So this is interesting because you've got several slides here. You got 3 slides here in the middle is what I'm looking at.
Okay.
So the top is an emu wing bone. So that's a comparative thing. You're comparing your Hesperornis, which is on the lower right here, to an emu wing, but you're also comparing it to a penguin.
Right. So in this exhibit specifically, it's not so much a comparison as it is talking about what studying the inside of bone can tell us.
Okay.
So the first one is phylogeny, which is a really fancy word for evolutionary relationships. So who's related to whom? So 2 fish are going to look more similar to each other than a fish is to a lizard. Just because of the amount of evolutionary time between when those different branches separated. So the phylogeny plays a big role. So all of these are birds, so they're all going to have characteristics that are similar among birds, like fast growth rate. So with the very few exceptions, I think the only two I can think of are king penguins and the kiwi bird. All modern birds, most modern birds, reach adulthood. So reach skeletal maturity, maximum size within 1 year of hatching.
So that's fast.
And yeah, I mean, and if you're talking about a songbird, you're talking about, 3 weeks.
Weeks, yes.
Yeah, but even an emu is going to reach what we call skeletal maturity or somatic growth within 1 year of hatching. So they don't lay down these quote unquote tree rings. So that's one aspect. The other is ontogeny. And ontogeny is the study of aging, essentially. So how an animal changes as it's between birth or hatching and death. And so if we think about humans, and if anybody out there has kids, or was a kid at one point, you're very well aware that kids grow very quickly, and then, there's kind of another little spurt up until puberty, and then we kind of tail off, and we have this asymptotic growth, and so we have an S curve, but we tail off at the end. So at some point, you really shouldn't be growing. We have a tendency to grow wider, but not necessarily grow taller at actually bone density.
That's just a measure of being happy.
Yeah.
I think.
So a juvenile bone is going to look very different than an adult bone, and that's what the penguin's showing. And then there's also biomechanics or functional morphology. So how a bone is being used is going to affect how that bone is growing. Right. So an emu, they really only use their wings like during courtship dances and stuff like that. They don't fly. Right. And so they don't have a lot of stress loading. They don't have to grow their rings really fast to be able to move and get food, versus something like a Hesperornis with their leg bones. They need those to kick, so they need those to fledge the nest, to hunt food, so whenever that parental care stops happening, they don't die. So we see, even within the same animal, we see different bones growing at different rates that can relate to how they're being used and kind of the lifestyle of the animal. And then the last one, so going back to that ecology aspect that I'm really interested in, is in environment. And this is one that's probably least studied and not very well understood. So how climate, environmental cues, so like change in photoperiod or change in the amount of light versus dark during the day. So we think about how that changes seasonally. You also think how that changes from like high latitude to low latitude. So how these different stresses, so whether it's migration or whether it's seasonality, like monsoon seasons, whether it's changes in growing seasons, how that affects how an animal grows. And so
how scary is that when you go into a field that hasn't been studied very much, and you're out there going, okay, I have to...
Right, so there are a lot of things to remember, and again, this goes back to the need to base our research and what we know from animals and ecosystems that we can study. And this is something that's really just now hitting its stride in the field of paleoecology, is that people got really excited and started cutting up all of these fossils without really ground truthing a whole lot of what we know from animals that we can actually observe. And so we're going back and filling in those holes. And so that's really changed how we understand mammal growth. And so that changes how we understand dinosaur growth, because when you get into something warm-blooded or cold-blooded, studying a lizard's probably not going to be as good of a physiological analog as a mammal.
Right.
And then when you just cut up like pigs and cows and humans, we're not good models for what an animal in the wild is going to look like in terms of domestication and stuff like that.
Wild things out here.
Yeah, so we do weird things to our bone because of the length of our life and our lifestyles. And so, there's really now this push of better understanding what modern animals do, how modern animals respond to dietary stress like starvation, how they respond to changes in the number of hours of light versus dark during a day, testing whether these rings that animals lay down are actual annual or whether they're just random, whether we can force them through starvation, which we can't, and other things like that. So we're really getting into this ground truth thing, and we're crossing, the people that are studying modern internal bone structure
Right.
are actually the paleontologists. Because
Right.
a biologist is going to go out and be like, hey, I'm going to watch that animal, and if I want to know how big it is, I'm going to pick it up and put it on it, or I'm going to tranquilize it and
observe
put
these
it on
things
the
in real
scale.
time.
Yep, you can measure how they're growing.
Right.
And, it's really just us as paleontologists, because we don't have the ability to put them on the scale. We don't necessarily know where all the fleshy bits go. So when we're doing size and girth and length, there are a bunch of question marks there in terms of our accuracy. So we look at bones to understand how old an animal was when it died, to understand how it grew. And so we're the ones that are looking at the modern animal bones.
Very cool. All right, so what else do we want to talk about this time around?
So why don't we, because we're pushing like 40 minutes.
Yeah, we've been on for a while.
So we'll segue into, again, I'm going to be on next week as well.
And I promise this is all leading into the Arctic.
It is.
It
So
really is.
I first approached Ian about wanting to help out one of these when we got into the Arctic, because I was fortunate enough in 2007 when I was working on my PhD to go to the Arctic. So I went to the Canadian Arctic, to Baffin and Violet Island, to do some paleontology field work. And it was really cool
pretty
because
cool.
when we're unloading the exhibit and opening the boxes, it was like a flashback. I was like, oh my gosh, these look exactly like what I got to see up there. So it's going to be a little bit more of a formalized slideshow, and we'll kind of do a little bit different with Facebook Live via Zoom, so I can show some of the pictures that I have compared to the artwork we have here. And then talk again a little bit about what I was doing up there and
Okay.
what we found.
So is there anything you want to get in while, what, are we running out of batteries? All right, so I guess we're going to sign off for today
Yep.
because I think our camera is about to
Yeah,
die.
but if people have questions, put them in the comments, and I'll come through and respond, and maybe address some of them next week if they're ones that should have a bigger conversation around them.
These live feeds take on their own direction. I wasn't planning on having as in-depth as a discussion, but that's what's really cool about these things, and that's really what I wanted out of this. So we will see you next Friday. I will be back with Dr. Wilson. Until then, take care of yourselves. Please like and share our feeds. If you know of anybody that's interested in this stuff, show this to them.
Great.
And we'll see you next time.
See y'all.
Bye-bye.